Welcome again to part 2 of section 12.8, which is about describing the curvilinear motion using the cylindrical coordinate system. If the particle moves in a space, well, 3D space, then where r, theta, and z changes with time, then we should use the cylindrical coordinate. Now, what's going to happen is that we will just add the z component to the position vector, velocity vector, and the acceleration vector. So it's indeed going to be very simple. So all what we have from the polar coordinate was that r, the position vector, was equals to the magnitude r by ur. So to have it in a cylindrical component, we have z by uz. Similarly, the velocity vector is going to be equal to r dot ur plus r theta dot u theta. That's what we had for the polar coordinate. And here we add z dot uz. For the acceleration, we will have a, which is equal to r double dot minus r theta dot square ur plus r theta double dot plus 2 r dot theta dot u theta plus z double dot uz. And that's it. Now let's have an example. So here what we have is a collar that slides along the smooth vertical spiral road, where r, the position vector, is equal to 2 theta and is measured in meter, where theta is measured in radian. If its angular rate of rotation is constant and equal to 4 radian per second at the instant when theta equals to 90, so this theta equals to 90, we want to determine the collar, radial, and transverse component of velocity, the collar, radial, and transverse component of acceleration, and the magnitude of velocity and acceleration. So let's start with the solution. We want to find the radial and the transverse component of the velocity. So we have been given that r is equal to 2 theta. And if we take the derivative of this, we will end up with r dot, which is equals to 2 theta dot. And r double dot is going to be equals to 2 theta double dot. Now, theta was given to us, which is equal to 90. So this is pi over 2. And it is measured in, of course, radian. Now, what is theta dot? It was also given to us. It was said to be 4 radian per second. So if we want to take the derivative of theta dot, which is 4, with respect to time, we will get 0 radian per second square. Now, we can find the position r, which is equals to 2 theta, by substituting 2 multiplied by pi over 2, and we will end up with pi meter. Now, r dot is equal to 2 multiplied by theta dot, where theta dot is 4. So this is 2 by 4, and what we get is 8 meter per second, and then r double dot is going to be equal to 0. So the velocity in the radial direction is equal to r dot, and this is going to be 8 meter per second. The transverse velocity v theta is equal to r theta dot, which is going to be equal to pi multiplied by 4, and this is going to give you 12.56 meters per second. Now, the velocity, the magnitude of the velocity is going to be equal to the square root of 8 square plus 12.56 square, and this is going to be equal to 14.89 meters per second. Now moving to the acceleration, AR is equal to r double dot minus r theta dot square, and I hope you remember the values from the previous slide. This is 0 minus pi by 4 square. So what we are gonna get? We are gonna get minus 50.24 meters per second square. Now A theta is equal to r theta double dot plus 2 r dot theta dot, which is going to be 0 plus 2 by 8 by 4, and this is going to be 64 meters per second square. So the magnitude of the acceleration is 50.24 square plus 64 square, and this is going to give you 81.36 meters per second square. Now let me extend the solution a little bit. It wasn't asked to find the directions, but if we want to do that, then if you remember, VR was found to be 8 meters per second, V theta was 12.56 meters per second, the magnitude was 14.89 meters per second, and if we calculate the angle theta, which is the tan inverse of V theta over VR, then what we are going to get? We are going to get 57.5 degrees. Now, on the other hand, for the acceleration, we got AR, which is equals to minus 50.24, A theta, which is 64, A is 81.36. So if I find the angle phi for the acceleration, which is the tan inverse of A theta, or A theta divided by AR, then I will get an angle of minus 51.81. Now, how do I represent these? So this is the radial direction. So I will extend this with the blue line. So this is the UR vector, and the transverse direction is going to be perpendicular to it. So this is U theta vector. So if we use the black to represent the velocity component, we are actually having VR right here, and we're gonna have V theta right there. Now the angle 57 over here, 0.5, is measured from the UR. So basically, tangent to this, we will have the total velocity vector, and the angle from here to there is 57.5 degrees. Now for the acceleration, it is different. What we have for the acceleration is that AR is negative. So AR indeed is actually going downward over here. That's AR. And A theta is going in the positive direction, so this is A theta. So what would you expect is that the acceleration vector is going to be somewhere here in between. And this is actually true, because measuring the 51.81 is actually measured in the negative sense. So instead of going in the counterclockwise direction, it has to be going from the clockwise. So either you measure that angle by from here as minus 51.8, or actually which is equals to this angle. So, and in that way you will end up with the acceleration vector right here. As I said, that's the total acceleration vector. Sometimes we have the path described by a trigonometric function, sine or cosine, and here we're just going to have a quick example just to show you how to deal with the situation. So if the position vector r is defined as 0.5 by 1 minus cosine theta, then the derivative r dot is going to be 0.5 multiplied by theta dot multiplied by sine theta. And what I did over here is basically I multiplied 0.5 by 1 and then 0.5 by minus cosine. Now the derivative, the time derivative of cosine is minus sine, so the minus with minus cancel. I have 0.5 as constant, so basically I take the derivative of cosine, which is minus sine, and then I have to take the time derivative of the angle, and this is why I get theta dot. And if you do this again, r double dot, then you will end up with 0.5 theta dot by cosine theta plus 0.5 theta double dot multiplied by sine theta. And what I did over here, I basically kept 0.5 and theta dot as is, and then I took the time derivative of sine. So sine theta, its derivative is cosine theta, and then the derivative of the theta is theta dot, and this is why I got double. Now on the other part, what I did, I kept the sine theta as constant, and then I took the derivative of this one. So 0.5 is still constant, so the time derivative of theta dot is theta double dot. To summarize, we have identified or defined the terms polar, radial, transfer, and angular direction. We also differentiate between the cylindrical and polar coordinate system. We identify the unit vector on the radial and transverse direction. We also talked about the angular velocity as well as the angular acceleration, and we derived their equation. That's it. Thanks.